Hi everyone. In today's video we are going to continue working with rational functions, and today we are going to be graphing them. In this video, you are going to think about determining domain restrictions for rational functions. We are going to identify discontinuities of the rational functions. Specifically, we're going to look at vertical asymptotes, horizontal asymptotes, and holes. And then we're going to graph the rational functions using the knowledge of those discontinuities. So let's first get started thinking about domain restrictions. Now remember, when you have a rational function, you cannot divide by 0 because that's undefined. So the denominator of our rational function can never be equal to 0. So that means x minus 2, our denominator, is not allowed to equal 0, and that means our domain restriction is that x is not allowed to equal 2. So if we think about this in terms of interval notation rather than as an equality, you could also say that the domain is from negative infinity up to 2, but not including it, and union with 2 up to positive infinity, but not including it. Another example of this is if you have this denominator, x squared minus 9x plus 14, we first need to factor that. It factors to x minus 7 times x minus 2, which means if this is not allowed to equal 0, because that would give us a denominator that equals 0, that x is not allowed to equal 7, and x is not allowed to equal 2. Thinking about this one in interval notation, that means x goes from negative infinity up to 2, but doesn't include it. It picks up on the other side of 2 and goes up to 7, but doesn't include 7. And then it picks up on the right-hand side of 7 and goes all the way to positive infinity. So you have two ways to write answers for there as well. The other case where there are domain restrictions with rational functions we've already done in Unit 6, and that's when the square root of a negative number does not exist. So let's go ahead and get into some of the vocabulary that we're going to need in order to do the graphing today. Remember that a rational function is a function that's written in the form f of x is equal to one polynomial p divided by another polynomial q. Keeping in mind the domain restriction, q of x cannot be equal to 0. The graph of this rational function is called a hyperbola. So just like in the quadratics unit we had parabolas, now in the rational function unit we have hyperbolas. And it's made up of symmetrical parts that are called branches. They are going to be symmetrical across a line of reflection, just like with the other symmetry we've done earlier this year with parabolas and things like that. Now, the thing that makes rational functions a little bit special is that there are going to be areas of discontinuity, where when you have an x value, it makes the denominator equal 0. And so weird stuff is going to happen at those points. So let's look at the two types of discontinuity. The first type is an asymptote, and you may also hear this called a non-removable or an essential discontinuity because they can't be taken out of the graph really easily. So if we look at this first example, f of x is equal to 1 divided by x plus 2, x is equal to negative 2 is not defined. It's not allowed to equal negative 2 because that would put a 0 in our denominator. So that's going to give us, at x is equal to 2, this vertical dashed line that's going to represent something that our graph is never actually going to touch because it cannot be equal to negative 2. This makes our graph discontinuous, meaning that when we draw these blue lines, we have to pick up our pencil and then put it down again to continue drawing the second branch of the graph. You'll notice in this one there's also a horizontal asymptote at y is equal to 0, and we'll get into that a little bit later on. The other type of discontinuity that we're going to have to look at is a hole in the graph. These are called removable discontinuities because if you fill in the hole with one single point, then you've got a continuous line. It's just one ordered pair that's missing, or more than one, but you can fill in these points or ordered pairs. So if we look at the graph of this one, we find ordered pairs by factoring and then dividing things out. So you can see in this next example, f of x, the numerator factors. And so what I've done here is factor the numerator here. And then you'll see that you have this x minus 2 in top and bottom. When those divide out, that's what creates the hole, because that has divided out. So you see over at x is equal to 2, because that's where this would be, there is a hole up here. And that hole is going to be indicated with an open dot on the graph to make that a little bit more clear for you on your screen. We'll talk more about how to find the y value of that ordered pair for the hole once we get to that part of the notes. Okay, so the asymptotes, like I was talking about a moment ago, they are going to be either vertical or horizontal for us. You can have oblique, which are these ones that go at a diagonal or slanted. All asymptotes are going to be graphed as dashed lines, and the curve is going to get really, really close to them, but it's never actually going to touch the asymptote. The exception to that is the horizontal asymptotes and the oblique. Sometimes weird stuff happens with them where it does something like this. But we'll get into that probably in a future math class. Okay, so let's look at asymptotes and finding horizontal asymptotes in particular. So to find the vertical asymptotes, you just look at what the domain restriction is, what x is not allowed to be, like we were doing in that first part. To find the horizontal asymptotes, there are three things that you have to memorize, and there are three situations. The first situation is when the degree of the numerator, so thinking about the exponent here, is equal to the degree of the denominator. So if we look at each of these examples first, you can see that for this first one, the degree of the numerator is 1 because that's x to the first power, and the degree to the denominator is also 1 because that's an x to the first power. So the two degrees equal one another. That's true in each of these examples. In this last one, you have a degree of 2 in the numerator and a degree of 2 in the denominator. So the degree is equal to one another, and that's going to tell us that our asymptote is going to be at y is equal to the lead coefficient of the numerator divided by the lead coefficient of the denominator. And this will give us the horizontal asymptote. Okay, so if we look at those three examples there, you can see that because the degree is equal on top and bottom, the lead coefficients are 6 divided by 3. And 6 divided by 3 is 2. And if we look at our graph here at y is equal to 2, we have a horizontal asymptote. Now, I do want to point out here that these are screenshots from a calculator, and calculators are not going to draw the dotted line. You have to be able to identify the vertical and horizontal asymptotes if there is one. So you can see here that after I've drawn that dotted line, it looks like both of the branches get really close to it, but they don't actually cross. They're not actually going to keep going up forever and cross over 2. They're always going to be less than y is equal to 2. If we look at the second one, the degrees are equal, so we're going to look at those coefficients. 3 divided by 3 is 1, so that means that the horizontal asymptote in this one is here at 1. And if I draw that dotted line in, you can see that those two branches never cross y is equal to 1. And in this last one, because the degrees are equal, the coefficients are 3 divided by 1, which means the horizontal asymptote is at y is equal to 3, which is here. And again, we can see that that arch shape that's happening never crosses over or gets larger than y is equal to 3. Okay, so that's the first situation. The second situation is when the degree of the numerator is less than the degree of the denominator. So you can see in each of these examples, down in the denominator, there is an x with a larger degree than whatever is in the numerator. So in this first one, it would be x to the 0 power, and 1 is greater than 0. And the second one, the degree of 2 is greater than the degree of 1. And in the third one, the degree of 3 is greater than the degree of 2. So when this happens, we are going to have two options. The first option, option A, is that if our function's equation looks like this, some number over x, then we're going to use this plus 0 that's on the outside. The HA, or horizontal asymptote, is going to be at y is equal to 0. The second option is if you have an equation that looks like this, we're going to use whatever k is. So notice here that these two equations look pretty similar, right? We have 0, 0 is hk in this first one, and whatever h is here, that's our h, and k is this number being added on the outside. So really we're looking for the k value in both of these situations because that's where our horizontal asymptote is going to be. So in this first example, h is 0 and k is also 0, so our horizontal asymptote is at 0. In this second one, we have h at 4 and k is going to be 0 as well. So we have an asymptote there. And if we look at this last one, h is 9 and k is 0, so we have, again, our asymptote at y is equal to 0. We're going to look at some when we practice where the k value is not just 0. The last situation is when the degree of the numerator is greater than the degree of the denominator, like in these two examples down here. Now, the good news is that we are not going to have a horizontal asymptote in these situations. There's going to be something a little bit more complicated going on that you're going to learn about in a future math class. I do want to point out for this example here, y is equal to x squared divided by x. Do you see how the x's divide out and that's equal to just x? That means that there is a hole at 0. So that's why you're getting this error message here. There is a hole at that point because it divides out. So our situation for situation number 3 is that you will not have a horizontal asymptote. Okay, so let's do some practice now. Let's just find the asymptotes and identify them either as vertical or horizontal. Now remember, vertical asymptotes have to do with the domain, and horizontal asymptotes have to do with the degree. Okay, so looking at this first one, y is equal to -3 over x. If we look at the denominator, that tells us that x is not allowed to equal 0, and that's our vertical asymptote. So that means then, let's look at these options. X is not allowed to equal 0, so that is this one, and it's our vertical asymptote. Now to find our horizontal asymptotes, I'm going to change my color here so things don't get too messy later as we do more of these. Remember, we're looking at the degree. The degree if the denominator is 1 and the degree of the numerator is 0. So that means we're looking at a less than situation. And the less than rule that we just talked about is that we are going to use whatever k is. And k in this one, number out here is 0, so that means y is equal to 0 will be our horizontal asymptote, which is this one. I'm going to identify it and write HA underneath. So let's look at another one. This next one, we'll look at that. It's x minus 3. It doesn't have anything in the denominator. This is going to be, if that's x to the first power, that's going to be a straight line. It's a linear function. Linear functions don't have vertical asymptotes because they don't have a denominator that we have to restrict for the domain, and they don't have a horizontal asymptote because they don't have any kind of discontinuity. So that one's going to be none. All right, let's look at this last one now. I'm going to switch my color back to red. The vertical asymptote happens where there is a domain restriction. So for our vertical asymptote, x is not going to be allowed to equal 3 because that would give us 0 in the denominator. So this one is our VA. And then if we look at our degree to figure out our horizontal asymptote, The degree for this one is another less than because the degree in the denominator is 1. The degree in the numerator is 0, so that means it's a less than, which means we're looking for y is equal to whatever k is. And in this one, we do have a k. Y is equal to positive 2. And that is our horizontal asymptote. Now, I do want to make a couple of really important notes here. When you write the equation of an asymptote, it has to be an equation. Y is equal to x, or for a vertical asymptote, x is equal to something. So please be sure that you're writing equations as y is equal to and x is equal to, depending on if it's vertical or horizontal. On your SOL test, they are going to mix these up, kind of like I have here in this one, where I give it to you as an x and a y. So be sure that you are identifying the correct asymptote. X's are the domain ones, so they're vertical, and y's are your horizontal, so they are going to have y is equal to. So be very careful with that element. You cannot just write 3 or 2. It has to be an equation with either x is equal to or y is equal to. Now, the last part of the discontinuities are the wholes, and we have kind of talked about this a little bit in this video already. Anytime that there is a common factor in the numerator and the denominator, that's when the two factors divide out and we make those slash marks. That's where a whole comes from. So wherever that x is that divides out, we need to find what the y is of the ordered pair and then draw that open circle to indicate the whole at that ordered pair. We can repair wholes by filling them in, and that is why they're called removable discontinuities, because we can take them out by simply filling in that one missing dot. Okay, so let's get to the actual graphing now. So the first thing we need to do is we always factor. So let's look at if we can factor either the numerator or the denominator. In this case, we can factor the denominator. So I'm going to factor that difference of perfect squares to x plus 3 times x minus 3. Okay, so now I need to find any wholes. So ask yourself, is there anything that divides out? There's not anything that divides out in this one, so that means there are no wholes that we have to worry about. The third thing is to look at the vertical asymptotes. So looking at your denominator, what is x not allowed to be? It's not allowed to be negative 3, and it's not allowed to be positive 3. That came from there. So that's where we're going to have our vertical asymptotes. Let's look at our horizontal now. For our horizontal asymptotes, we have an x squared on the top and the bottom. That means for our horizontal asymptote, we're going to use the coefficients. Y is equal to 2 divided by 1, which means y is equal to 2. So now we have lots of asymptotes, 3 of them. Let's go ahead and draw them as dashed lines. So let's see, I'm going to do my horizontal one here in blue. So that's at y is equal to 2, which is there. So I'm going to draw a horizontal asymptote there. Now I'm going to do my vertical asymptotes next. And my vertical asymptotes were at x is not equal to negative 3, which is here, and positive 3, which is here. So I'm going to draw some dashed lines to indicate those vertical asymptotes. Okay, so now I have my asymptotes and I'm ready to plot points. Now, for our purposes, we are going to plot points using the calculator because these can get very messy, and our goal this year is not to necessarily worry about that kind of messy. So I'm going to go into my y equals and I'm going to plug in the original problem. I have 2x squared divided by, and then I'm going to put my denominator in parentheses. You should always put your denominator in parentheses. This way your calculator will do order of operations correctly. If you have pluses and minuses in your numerator, I would also put it in parentheses. If you want, you can always put the numerator in parentheses and the denominator in a second set of parentheses. Okay, so I'm going to hit the graph button. We're going to get a sense of what this shape looks like. Do you see how it's curving up right there and then picking up again? The space in between, here, here, and here, those are the asymptotes that we had just graphed. So now it looks roughly like this parabola here is going through 0, 0, but I want to be a little bit more careful than that. So I'm going to go to second graph to look at the table and pick the nice points here. You'll see that there are error messages at certain values. That's where your asymptotes are. At x is equal to 3, we have this asymptote, and that's why we're getting an error there. Okay, so I'm going to scroll up some to the other side. There's my other vertical asymptote, and let's try and pick some nice points here. It doesn't look like I have anything super nice, but at -9 I've got 2.25, which is 2 and a little more, so let's do that one. I'm going to switch my color again. Let's go with black this time. So I'm going to go to -9 and then up 1, 2 plus a little bit more. Let's see, the -7 is almost at 2.5, so let's go to -7 and then 2.5. If we keep going at -5, it's a little more than 3. 1, 2, 3 plus a little bit more. And then at -4, it's a little more than 4.5. So -4, 1, 2, 3, 4, and a little bit more. So you're beginning to see there that we have this curved shape. Remember, it's going to approach the asymptotes but not touch them. So I'm not going to cross those dotted lines when I draw this. Now, if I go scrolling back down some so that I can do that parabola that opens down, it looks like I have 0, 0 as my vertex. So over here, I'm going to plot 0, 0. And then I'm going to pick some other kind of sort of nice ones. So it looks like it's at -1 and then down just a quarter, +1 down just a quarter, and then at 2, it's down 1 and a little more than a half. At -2, it's down 1 and a little more than a half. So that's going to give me that part of my parabola. Okay, so we have one more section. We have the far right to do, so I'm going to scroll down a little bit more to get some nice numbers. I'm going to the right-hand side, or the positive side of x is equal to 3, which is where that vertical asymptote is. It looks like at 4, it's a little more than 4.5, so that's about there. At 5, it's a little more than 3. At 6, it's a little more than 2.5. And at 7, it's not quite 2.5. Okay, so again, I have this nice kind of symmetrical curve there. So notice here you have all 3 branches. Part of it is a parabola, and then you also have these other 2 branches that, to make our full hyperbola. So there are 3 pieces with a bunch of discontinuities, those lines there. So now what I'd like to do is just go through and do a few practice problems, because there are a lot of steps to graphing these. You are going to have to be able to talk about asymptotes and discontinuities like holes without a calculator. And so we're going to practice doing those without, and then we'll use the calculator to get our plots so that or points so we can plot them and then draw the branches in. Okay, so the first question, remember, is does anything factor? And looking at this one, there's nothing that factors, so I'm ready to talk about my vertical and horizontal asymptotes. Remember, the vertical asymptotes have to do with the domain. X is not allowed to equal 0, which means here x is not allowed to equal 0. That's going to put my vertical asymptote right on x is equal to 0. And then when I look at my horizontal asymptotes, I am asking myself, what about the degree? The degree of this one, the numerator is bigger, so that's a less than, which means y is equal to whatever k is. There's no number being added out on the front, so that means that y is equal to 0. I just realized one quick mistake that I want to fix. Do you see how I said x is not equal to 0? The vertical asymptote is that x is equal to 0. So I'm going to change that sign to be a equal to sign. The domain is that x is not equal to 0, but the vertical asymptote is at 0, so that should be an equal. Okay, so now let's go back to my horizontal asymptotes. Y is equal to 0 is my horizontal, so I'm going to draw the dotted line there. And now I'm ready to graph because I don't have any holes to worry about since nothing factored out, and I have my asymptotes. So if we pull our calculator back over and go into our y equals, I've got 4 divided by x, and so I'm just going to go straight to the table so I can get my nice numbers here, or nice-ish numbers. Okay, so let's see, at 0, that's one of my errors, so I want to be up on one side of it. Oh, there are some nice numbers here. So at -1, it's going to be down at -4. And at -2, it's going to be down at -2. Now, I could go a little bit further, but with those 2 points, I can see roughly that's the shape I'm going to get. And if I look at the other side, at 1, it's up at 4. And at 2, it's at +2. That, again, will give me enough, those 2 points, to get a rough shape going of what my hyperbola looks like. Okay, now I do want to think about domain and range for this one. If we look at the left and go left to right for domain, this goes infinitely to the left, right? So it starts down at -infinity, and then it gets stuck at 0, right? Because that asymptote is there and it never actually touches it. Then it picks up over here on the other branch, the branch on the right, on the other side of 0, and it goes to +infinity. The range is going to do something similar here. It goes down forever, so it starts at -infinity, but then we get stuck at this horizontal asymptote because it doesn't ever touch it. So it doesn't include that horizontal asymptote at 0, and then it picks up on the other side of 0, this part down here that's getting really close, and goes up to +infinity. For increasing and decreasing, we are only ever going to, in graphs like this with 2 branches, either be increasing or decreasing. Ones like that previous problem we did with that parabola, you're going to have a little bit of both. So if we think about this one, if I was on a bike over here, I would be going downhill the whole time, right? And then if I was on a bike up here, I would be again going downhill at a kind of scary angle. So this is all decreasing. It is never going to be increasing. Now, the decreasing that's happening starts out at -infinity, because remember, decreasing and increasing are talking about the x's read from left to right. So it's decreasing all the way up to 0, but then it skips 0 because of that asymptote and decreases from 0 to +infinity. That's this right branch. All right, let's do another one like this. So the first thing I need to ask myself is, does it factor? And this one does not factor at all, so I don't have anything to divide out, no holes to worry about. For my vertical asymptotes, I need to think about what x is not allowed to be. The domain is going to be that x is not equal to -2, because that would make it 0. So that means we have a vertical asymptote at x is equal to -2. Oops, drawn this the wrong way. At x is equal to -2, that's there. Okay, and then for my horizontal asymptotes, I'm asking myself about the degree of the numerator and denominator. This one has a degree that's less than the denominator, so that means I'm going to use y is equal to k, and k is equal to -3. So I'm going to have my horizontal asymptote at -3. Okay, with my 2 asymptotes now, I'm ready to plug this in and get some points. I'm going to put the whole fraction in parentheses. So 1 divided by, and then my denominator in parentheses, because it's got that plus sign and I need to keep x plus 2 together. Then outside of my parentheses entirely, I'm going to put that -3. I'm going to hit second graph to see where things are happening. I'm going to pick nice points here. Now I have my vertical asymptote there at x is equal to -2, so let's pick some things on the left and right. I have -3, -4. So down to -3 and then down to -4. That puts me there. And I have -4, -1, 2, 3.5, which is going to put me there. And that roughly gives me enough to draw that shape. On the other side, I have -1, -2. And I have, let's see, 0, -2.5. So that's really close to that asymptote. That gives me this branch, Again, not ever actually touching my horizontal asymptote. Okay, so let's think about range, bottom to top. My bottom is down to negative infinity, but then I get stuck at y is equal to 3 and negative 3, and it doesn't actually touch it. The other branch picks up on the top side of negative 3, and it goes up to positive infinity. Oh, goodness. Okay, so then ask yourself this question. Is this one increasing or decreasing? It's going downhill, reading left to right, and then it's going downhill again, reading left to right. So that means this one is decreasing everywhere and never increasing. So the decreasing is happening everywhere except for at x is equal to negative 2, which means our decreasing is negative infinity to negative 2 in union with negative 2 to positive infinity. Okay, so let's look at two more of these because it's a whole lot of steps to graph. All right, question number 1 is, does this factor at all? And this one does factor. It has a GCF in the numerator. So let's take out that GCF of 3, which leaves x minus 2. Okay. That does not have any holes because those do not divide out from one another. They don't match, so we still have no holes to worry about. Now, we do still have asymptotes to worry about, so we're going to look at our domain for our vertical asymptotes and ask ourselves, okay, if the domain is that x is not allowed to equal negative 2 because it would make us divide by 0, that means there has to be a vertical asymptote at negative 2. When we look at our horizontal asymptotes, look at this one. It is a little bit different. For this one, the degree is equal, which means that we're using the coefficients. So y is equal to 3 divided by 1, the coefficients of those degrees. So that means we have a 3 there, and our horizontal asymptote is going to be right there. So let's look at our calculator and get some points now. Plugging this one in, I'm going to plug in the original problem, and I'm going to use parentheses on the top and also the bottom. So 3x minus 6 divided by x plus 2. Okay, and then I'm going to hit second table. Okay, so let's see. This one has some nice points, so let's pick some of those nice points. Let's do negative 6, positive 6. And we've got negative 5, 7. And we can also do for positive 9 if you want. And that's going to give us a branch that looks like that for our hyperbola. Okay, looking down at the other side, I've got negative 1, negative 9, and 0, negative 3, and 1, negative 1. So that gives me roughly that branch. Whoops. Okay, so let's talk domain range and increasing, decreasing now. Our range at the bottom, because this goes down forever, is negative infinity. It gets stuck at the horizontal asymptote of 3, picks up on the other side of 3, and keeps going up to positive infinity. For this one, if I'm reading it from left to right, I am increasing on this branch, and left to right, I'm increasing again. I'm going uphill. So that means I am never going to be decreasing. And the increasing, reading from left to right, starts at negative infinity. It stops increasing at the vertical asymptote at negative 2, but then it picks up on this other branch at negative 2 and goes to positive infinity. Okay, let's do one last problem, and this one is going to have a hole in it. So remember, the first question is always, does it factor? And the answer is yes, it does. So let's do some factoring. We have x plus 3 times x minus 3. And in the denominator, we have x plus 3 times x plus 5. Okay, so do you see how x plus 3 divides out? That means that is a whole. The whole is going to happen at negative 3 something. X is equal to negative 3 there, and I'm going to have to find what that y value is. But when I graph down here, special stuff is going to be going on at that point, negative 3 something. Okay, so now let's go ahead and do our asymptotes. For our vertical asymptotes, we know that, and we're working with the leftovers here, by the way, so we're working with this equation to figure out where our asymptotes are. X for our domain is not equal to negative 5, right, because that would mean we're dividing by 0, which means that we have a vertical asymptote at x is equal to negative 5. Okay, then for our horizontal asymptotes, we have equal degrees on top and bottom. And if our degrees are equal, that means that we're using the coefficients. So 1 divided by 1 means y is equal to that coefficient of 1. So let's draw that horizontal asymptote. All right, so now I'm going to go to my calculator and figure out my nice points, and I'm going to have to keep this whole in mind up here. So let's see. Let's put in our numerator in parentheses, x squared minus 9, and our denominator in parentheses, x squared plus 8x plus 15. Okay, so notice here I used the original problem and I put parentheses around both the numerator and the denominator. Let's go into the graph now. So looking at this one, oh, do you see that there are two error messages here? There's one at negative 5, which is where my asymptote is, and there's also one at negative 3. That's where my whole is. So let's get some other points on the graph, and then we'll talk about what to do about that whole. Okay, so if I look at the left-hand side, at negative 7, I'm going to go up to 5. And at negative 6, I'm going to go all the way up to 9. So that's going to give me this branch here. Now let's look down at the other side. We have negative 4, negative 7, which is there. And we have negative 1, negative 1. And for one more, let's do 3, 0, because that'll give us an x-intercept. Now, I am not going to draw this line yet because I still have to figure out where exactly that hole is. Now, you have a couple of options here, and we're going to be using this leftovers after I divided out the whole. You can either plug in 3 or negative 3 to these two spots and see what it's equal to, or we can, in our calculator, look at, instead of the original problem, this problem, x minus 3 divided by x plus 5. Because what we've done here is we have divided out the whole. We've taken out or removed the discontinuity. So if we look at the table now, we're going to have the same points, but we're not going to have an error message at negative 3. Do you see it, how it has that negative 3, negative 3? That means then that this whole is at negative 3, negative 3. So knowing that, then I can plot with an open circle there. Be very clear about your open circle. And then I can draw my branch that does not go through but skips over that hole there. Okay, so let's talk about our domain range increasing, decreasing here. Now we need to do a little bit more with our domain because this whole is not included. That means x is not equal to negative 3. So our domain is actually going to be coming from this full denominator, not just the leftovers here. So we're right that it's not equal to 5, but it's also not equal to negative 3 because of that whole that's happening that gets skipped over on our domain. Our range is also going to have some funny stuff going on. It starts down at negative infinity, but then there's that hole at y is equal to negative 3. So it jumps over that point, not including it. It picks up on the other side, the top side of the hole, and it goes up to the horizontal asymptote, which is at 1. and then it has to skip over the asymptote, and this branch picks up on the positive side of 1 and goes up to positive infinity. For increasing, this one is increasing this branch from left to right, and this one is also increasing from left to right. So we need to list that, but we need to be careful here because we've got stuff going on. So the increasing starts at negative infinity and stops at our asymptote negative 5. Then it picks up on the other side of negative 5, that's this part here, but it has to jump over this hole at negative 3. It jumps over the hole, and then it continues increasing to positive infinity. The decreasing is going to happen never. Okay, so that is a bunch of examples. I'd like for you now to try some practice. You should now be able to figure out the domain restrictions for rational functions, and that tells you your vertical asymptotes, and then you can identify the other types of discontinuities as well, the vertical asymptotes, but also the horizontal and the holes. And then using all of those discontinuities and the calculator a little bit, you can graph those rational functions. So give those practice problems a try now.